So we are going to be looking at barcodes, which are a way for us to look at the topology of data. Data is often presented as an unordered sequence of points in a Euclidean n-dimensional space, which we denote with a blackboard bold E to the n. So we wish to provide a way to analyze this data using simplicial complexes. These are the main tools we've used throughout this quarter, so being able to look at information presented in this way is very applicable to us. So the most obvious way to convert a collection of points, x sub alpha, in a metric space into a global object is to use the embedding in En as the vertices of a combinatorial graph whose edges are determined by proximity. This proximity is determined by some specified distance epsilon, and depending on our choice of epsilon, this is going to affect what our simplicial complex will look like. So then to complete the graph into a simplicial complex, the choice of how to fill in these higher dimensional simplices of the proximity graph lead to different global representations. The two most common are the check complex, which is denoted C sub epsilon. So given a collection of points, x sub alpha, in Euclidean space En, the check complex, C sub epsilon, is the abstract simplicial complex whose k simplices are determined by unordered k plus 1 tuples of points, x sub alpha from 0 to k, whose closed epsilon over 2 ball neighborhoods have a point of common intersection. C epsilon is also known as the nerve. So our check complex is sometimes called the nerve because everything has to kind of be connected to a central kind of point and they all branch off from there. Our other complex is called the Rips complex, denoted R sub epsilon. So given a collection of points, x sub alpha, in Euclidean space En, the Rips complex, R sub epsilon, is the abstract simplicial complex whose k simplices correspond to unordered k plus 1 tuples of the points, x sub alpha from 0 to k, which are pairwise within distance epsilon. So the check complex is a topologically faithful simplicial model for the topology of a points cloud fattened by balls. However, the check complex is difficult to compute because you have to be very precise with the epsilon and which points are in or out of the closure of it and how many of them are shared. But from a computational outlook, the Rips complex is less expensive computationally, even though it has more simplices than the check model in general. And this is because the Rips complex is maximal among all of its simplicial complexes, given its one skeleton. So the combinatorics of the one skeleton completely determines the complex that we are given. And we have a picture to kind of show the difference between the two. So here we have our collection of points in En. And here we have the epsilon neighborhoods, or epsilon over 2 neighborhoods of each point in each vertex in our space. And we can see with the check complex that if we look here, let's actually get a pin so we can see what we're doing. If we specifically look at those 3 vertexes, we see that they overlap ever so slightly here and here and here. So for the points corresponding to that here, we're all just going to have lines between them because there's no point of common intersection of these neighborhoods of all 3. So that's why there's nothing filled in there. Versus with the Rips complex, looking at those same points, come on, there we go, here, that we were looking at, we see that it is filled in because each one of the vertexes are within epsilon of each other pairwise. So we get to fill them in. And we can see that for both of these, the Rips complex is more filled in general than the check complex. So it's a little bit more filled out, but it's a little easier for us to look at and say, oh yes, obviously these points are going to be connected because they're within an epsilon or within that neighborhood, a distance pairwise with each one. So it's a little easier for us to create the complex. But how do we choose our epsilon? That can be a big question. For a sufficiently small epsilon, the complex is just the discrete set of vertexes. And for a sufficiently large epsilon, the complex is a single high-dimensional simplex. So there's got to be a point in between the two that is going to be optimal, or at least that's what we would hope or want. But sadly, in general, there is no optimal epsilon. As we're going to see in the next segment, we're going to look at some times when an epsilon grows so large that we remove small holes that we feel like are not important. But the problem is that large holes distinguishing the annulus from the disk become filled in once we close up those smaller holes. So while it might appear that just from looking at it, oh, we should be able to mess with this enough to create an optimized epsilon, actually finding it can be really, really difficult. All right, so in the next section, we're going to look at some different cases with looking at our two Glober models.
Okay, once we have established the idea of a RIPS complex here, we want to direct our attention to an example. So what this example is showing is an annulus and a RIPS complex being generated by it. So we can see from here, in this first example, we choose a relatively small epsilon here, and the way that the simplicial complex is created here is with the intersections of each of these epsilon balls surrounding the points inside of our annulus. Now, as we can see, when 2 points are over, or when 2 epsilon balls are overlapping, or when only 2 epsilon balls are overlapping, we get these one simplexes attached between the vertices there, creating these sort of connected components. Now, within these connected components, we can find holes, which we will eventually see compute into a homology group. But another thing to notice is something like this triangle over here, a 2 simplex that's created over the intersection of 3 points. So once we've established this, as we can see as we increase epsilon to the next example, we get more connections between the vertices, right? There's some extra connection over here and there and here, and then it all actually ends up becoming one component. In the next one, we start to see a little bit more overlap, where the epsilon balls increase greater and greater to sort of close in some new holes. So as you can see here, this new hole has been created, whereas it didn't exist in this example, or for that epsilon. Now, continuing further, as we increase again, we start to see many more 2 simplexes appearing over here, and we're only left with one hole in the middle. Now, at this epsilon here is the one that I think most accurately describes the annulus. But as we can see, if we increase epsilon even further, that hole actually closes up here. And as we do it further, it just keeps closing and stays closed. So we end up getting a simplicial complex that is, or a RIPS complex that has varying meaning depending on what your choice of epsilon is. So the question that we're trying to answer is, how do we know what holes are relevant and which ones aren't? Because what we're seeing is holes appearing and then subsequently disappearing. So the homology groups of each of these complexes is going to be different. Now, what we actually find is that just choosing some epsilon and computing the homology isn't actually going to give us anything about why the holes, or about which holes we should focus on and which ones are relevant, because it's not necessarily just an optimization problem of trying to find the particular epsilon, because you have no frame of reference, right? We can tell that this example here is probably going to be the one that gives us the most accurate description of the homology group, but there's no way of knowing just from epsilon. So in order to do that, we need to introduce something called persistence.
Of simplicial complexes is called filtration. And so some holes may appear and disappear, and the persistency of these homological features are considered as features of the data set. So essentially the essence of what persistent homology is to track the birth and death of these homological features in kx delta for different delta values. So essentially in filtration, one can record the birth, which is the time that a hole appears, and the death, which is the time a hole disappears of holes. And then the lifespan of each homological feature can be represented as an interval, where the start and end points of the interval correspond to the birth and death, respectively. And then that gets into the idea of barcodes, which we'll be seeing soon. But here's an example of like a filtration. So we see here, starting at 0, we just have like those 4 dots. And then as we progress, we get holes. And then those holes are essentially like removed as we increase our delta. So we'll see next how barcodes work.
All right, so basically what we're going to be doing with this piece is, given some point cloud of data, how can I represent this data with simplicial homology or model it? What we're going to do is, given some point cloud right here, we will create a RIPS complex, which the way it works is first we need a metric space so I can define distance between my points. And once I have this distance, I fix some constant r, and I create a simplex in my complex if every single point in that simplex is less than r distance from each other. So for example, if I have these 3 points in my cloud, the top point is farther than r distance from any point, so it will remain by itself in my simplicial complex. But on the bottom here, these 2 points are closer than r distance away from each other, so we combine them into a line in our complex. One other complex that we have is the cache complex, which is similar to the RIPS complex. We still use a metric and a r distance, but now we create these r/2 balls, where we create a simplex if there is a common point in every r/2 ball, aka all of the balls intersect. So still this top ball, no intersection, we'll leave it alone on the right here in the simplex. But these bottom 3 balls are all intersecting at this tiny little circle point here. So we will combine them into a triangle in my simplicial complex. So think about cache complex versus RIPS complex. Although the cache complex is considered a better representation of the data, it's much more computationally expensive. So we'll be sticking with these RIP complexes. And essentially what we're going to be doing is creating a filtration of these complexes. But first, you have to define what a filtration is. So first of all, I start with r equals 0, and we consider r equals 0 to be the empty set. And as we increase r slowly, we will create another complex, k0, which will be at this left one here, every point by itself. As we keep increasing r, we keep on creating more and more complex simplicial complexes, until eventually with our last complex, big enough r, every single point is in one simplex. So if I have this example down here where I have 4 points in my cloud, again, the first one with really small r, none of the points are within r of each other. So we'll just get this k0 with all the points alone. Increase r slightly. I see on the bottom left here, these 2 points are within r of each other, but the rest are not. So I'll create one line in my k1. In this right example with a bigger r, I guess I'm representing these balls as r/2 balls. So intersection is there within r of each other. With a big enough r, these 3 points are all pairwise less than r distance apart. So I can combine them into a triangle down here, and this point on top is still alone. With r large enough, all of these balls are going to be, or all these points are going to be within r distance of each other. So my last case, my kn in this case, will be a 3 simplex, where again, every single point is combined into one simplex. And sort of the deal with this is I'm creating this filtration with all these different r values. Which of these filtration complexes do I actually care about, or which one actually represents the data? And the answer to this is actually none of them. There's not really a best choice of r to model the data. What we're doing instead is we're going to be using persistent homology and say, okay, if a feature is important, it's going to be lasting for a long time, for a long amount of R values. How long does each feature last? And I'll explain what that means in a second. And we're going to analyze this with a barcode. So let's say we're looking at this point cloud on top. For some R value, let's look at this second picture here. This 2 simplex here, this triangle was birthed or created. So these 3 points are combined into 1 simplex. We're increasing R again, we still have this triangle. Increase R again, we still have this triangle. Increase R again, in this picture right here, this triangle has died. It is now combined into some sort of complex that is bigger than a 2 complex. So the second picture was the birth, and this 5th picture was the death. And we consider a feature important if it has a long interval down here. So each of these intervals or barcodes, the start of a barcode, let's say I'm looking at this one right here in H1. For this R, which was represented as epsilon in this graph, for this R value, the feature was birthed. And right here, our feature died and was recombined into something larger. So we're using this persistence barcode in these intervals, these birth-death intervals, to say, okay, if a feature is birthed and death in a really short amount of time, like say this one, this is just noise in the data. We're not considering this little piece to be part of H1 at all. It's just nothing. But if a feature persists, for example, this H naught generator right here, we consider this feature to be very important to our complex. So again, each snapshot in time here, let's say I'm picking this epsilon or R, I can see I have 1, 2, 3, 4, 5, 6 generators in H naught, which we're considering 6 zero-dimensional holes. And this one that persists is the most important zero-dimensional hole.